Today, our discussion will be about topic 12.3a, aqueous inorganic chemistry. This is an extension of our discussion about complex metal ions. And now we're going to look at complex metal ions that often begin as a transition metal in the center surrounded by water molecules. The assessment criteria for this activity is as follows. We're going to recognize various acid-base theories and understand the conditions in which each may be used and their strengths and limitations. We're going to understand ligand substitution with similar and dissimilar sized ligands and the consequent changes of coordination that come about as a function of the change in size of the ligands. We're going to recognize the existence of more than unidentate ligands and understand a topic called the chelate effect. And we're going to be able to explain ligand substitution in terms of complex ion stability. One of the first things we have to do is look at the acid-base theories that we already know and see that we're going to have to look at complex metal ions a little bit differently. What do I mean by this? Well, in the Arrhenius theory, acids were defined on whether it contained hydrogen or an OH group. In the Bronsted-Lowry theory, we looked at acids being proton donors and bases being proton acceptors. What do we do when we have a transition metal surrounded by water molecules in dative bonds? It's hard to find something that contains hydrogen. Does that mean the water on the transition metal is acid? What does that make copper? Or can we see it as a proton donor when in fact the oxygen molecule is the one that is attaching itself to the transition metal? The Lewis theory defines acids as electron pair acceptors and bases as electron pair donors. So, let's think about a complex metal ion in terms of electron pair acceptors or electron pair donors. What does a transition metal do to create a dative bond? It accepts the electron pair from the oxygen in the H2O to create the 6 water molecules around the transition metal. So it has accepted an electron pair, so complex hexa-aqua ions are acids. We couldn't have defined them using the Bronsted-Lowry theory or the Arrhenius theory. Here we have a listing of possible ligands and their coordination number. Ligands vary in size, so the ability to place themselves around a transition metal decreases as the size of the ligand increases. As you look down the list of coordination numbers, you'll see that chlor is one where we can have a very small coordination number. The majority of other ligands are in the 3, 4, and 6 category, with 4 and 6 predominating. But ligand substitution is determined by the size of the ligand. And we'll see more about this when we talk about this in class.
That we don't have to name these things, but there are some names here. So common coordination number 6. Okay, so these two here both have a coordination number of 6 because there are 6 coordinate bonds. We've just seen the hexaaqua iron 3 ion. Here's a hexacyanoferrate 3 ion drawn here. Okay, we've got 6 ligands. The ligands here are cyanide ions, so Cn minus. Okay, and because each one of them has a negative charge and there's 6 of them around an Fe3 plus ion, overall the charge is 3 minus. So again, we don't have to name these things, but we would have to be able to write a formula. If we were given a diagram, we'd have to be able to figure out the charge of the complex if we knew what ligand was coordinating to a particular acceptor and how many of those ligands there were. And I suppose here we can also see that coordination number 6 complexes often have this octahedral geometry which we introduced in the bonding topic. Here's an example of a coordination number 4 complex with 4 coordinate bonds. Here the coordinate bonds are between chloride ions, the ligand, to the acceptor, the copper 2 plus ion. How do I know this is a copper 2 plus ion? Well, the name tells me that's one thing, so this 2 actually refers to the oxidation number of the central ion. But I can also figure it out from the charge on this complex, because I know that a chloride ion has a charge of 1 minus. I've got 4 of them, and in total the charges add up to 2 minus, so this copper must have been a 2 plus. And again, here's the name of it, but we don't need to worry about that. There's also possible to have a coordination number of 2, and there are other coordination numbers which we're not going to go into here, but here is an example of a coordination number 2, and this is the diamine silver 1 ion, so ammonia here is the ligand coordinating to a silver 1 plus ion. Why is the complex 1 plus overall? Because ammonia doesn't have a charge. So in other words, if you were asked to figure out the charge on the silver ion, you'd know it was 1 plus because your ligands are all electrically neutral here. As far as the shape goes, it's now linear because these 2 coordinate bonds will get as far away from one another as possible on this silver sphere. You might wonder how we know this is tetrahedral, because you can in fact have square planar geometries. That's not something to worry about with coordination number 4. If you drew this as a square planar complex, you'd actually be okay, but it's actually tetrahedral, this particular example.
This objective asks us to recognize the existence of bi- and multidentate ligands and understand the chelate effect. If we talk about water, it is a unidentate ligand. That means around one transition metal, we should be able to get 6 water molecules in dative bonds. Multidentate ligands have more unshared pairs that they can share with the transition metal ion. EDTA is an example of a hexadentate ligand. That means it has 6 unshared pairs it can share with the transition metal. Once we use something for like EDTA, instead of water, we replace 6 water ligands with 1 EDTA ligand. And you can see as an example what happens when we do replacement reactions, the ligand substitution reactions with ammonia. Each time we replace a water ligand with an ammonia ligand, we create more waters. When we create more waters, it looks like on both sides we have the same number of characteristic molecules. This is an example for a unidentate ligand. What would happen if we used a bidentate ligand? If we used a bidentate ligand, we would have more molecules of product than we would of reactant. That means that the entropy of the products has increased. That means that the reaction favors the use of a multidentate ligand because the products are more random and therefore there is more entropy. The chelate effect is using some multidentate ligand to remove harmful metals from the body. For example, if the complex metal ion was lead and we could use EDTA to surround it, once that complex metal ion got to the liver or kidneys, that part of the body would not recognize EDTA as being helpful to the body, and it would be released from the body. Now, here's a little bit easier discussion of ligand substitution. We said that there is more entropy. That is because the multidentate ligand displaces more than one molecule in a ligand substitution. That increases entropy. An increase in entropy makes the formation of a chelated complex more favorable. Again, look at the substitution by ammonia. We have the same number of molecules on the left-hand side as on the right-hand side. That doesn't encourage stability. What encourages stability is the use of multidentate ligands in a ligand substitution reaction. Here are some questions to start your thinking. Regarding our definitions of acid and base theories is question 1. Talking about ligand substitution are questions number 2 and 3 regarding entropy and regarding the chelate effect. Talk to you later.